Are you interested in Snowflake for Data Lake? In today's video, we'll be showing you how Snowflake enables Data Lake and other storage patterns, sharing new innovations, and we'll be performing some really cool demos to show you how you can store unstructured data inside of Snowflake, perform data lineage, and impact analysis. Sit tight, we're getting started now. Hello and welcome. I'm James Malone. I'm a senior manager of product management here at Snowflake. Today, I'm joined by Saurin, who's going to talk about unstructured data and some of our new innovations in data storage. And I'm also joined by Raja, who's the lead for data governance. In this session, you'll hear about the latest and greatest from Snowflake and data lakes. But you also hear about our vision for how we build data lake and storage products, and how we envision Snowflake being a data cloud that's more than just a data lake or a data warehouse. And of course, you'll see some great demos about our latest innovations. With that, let's dive in. So even with the proliferation of cloud technology, data lakes have become much harder to implement. It's really no surprise that data lakes have their challenges when you look at all of the facts. First, with the expansion of cloud technologies, it's still really hard to centralize your data. I'll give you a few reasons why. First, data can be separated by its structure. So you may have structured data, unstructured data, and semi-structured data. Typically, you use different tools and different methods to work with all of these types of data. This can silo your data. Second, you can silo data by a given cloud or a region. This makes it really hard to share data, even within a company or between companies. Three, a lot of people like to use different tools to work with the different types of data, and this further silos data because now you have to think about how to ingest data, move data around, and try and structure data so it's usable by everybody inside of an organization. Four, different cloud providers have a whole suite of different tools, so it's really complicated to decide which tool to use, how to use it, and how to make it work with your data lake. To account for all of these data silos, data engineers have tried to come up with solutions. If you've handled storage, processing and querying that data is still either slow, expensive, or both. And data engineers have had to create complex ETL pipelines that are slow, error-prone, and make it really hard to share data between your data lake or data mesh and other data lakes, either within your organization or outside of your organization. And with a lot of systems, governance and security and control of your data has become really difficult. This is a risk for compliance because it makes it really difficult to know who has access to what they're doing with it, how they're using it. It makes it really difficult to determine data quality, what type of data you're working with, how good is the data, how fresh is the data. And three, it makes it really hard for users to find data, to understand data, and to get data that they need to solve a business critical problem in a short period of time, and then collaborate with others working with that data. So just to recap, even though there's a lot of new technologies and cloud has definitely helped, it's also in some ways made things really difficult when you're trying to work with data storage and data lakes. The data cloud is one global unified system connecting companies and data providers to the most relevant data for their business. So what does that mean for your data lake? Well, there's a few things. With Snowflake, you can bring all of your data together in one place. One of the killer features, I think, of Snowflake, and one of the reasons why I personally love Snowflake, is you can work with structured, semi-structured, and unstructured data all in one place. From a set of storage technologies, this is really powerful because you're not thinking about fragmenting your data between different silos and data lakes because of the type of data that you want to work with. This allows you to greatly simplify your architecture and have a much better view on your data and generate insights on top of your data. It makes it very easy to take all of your data and put it in one place, which often is the goal for most organizations that are creating a data lake. They're trying to create a one-stop shop to store and serve their data. Snowflake allows you to do this because we work with all types of data flexibly and natively in one set of tools. Second, Snowflake is very fast and very efficient. And this really matters when you want to use data inside of your data lake. Snowflake is elastic, so you can support workloads with speed and reliability. This means you can scale up quickly and scale down to zero automatically. Virtually, there's no concurrency issues in Snowflake, so you don't have to really worry about concurrency and maintenance. If you've worked with data lakes inside of cloud blob stores, Concurrency is probably one of the subtle problems that you've encountered. It can be really difficult to get a good view of data, what data is inside of a blob store at a given period of time, to be able to work with that data. So the fact that Snowflake is both elastic and also solves for concurrency problems out of the box is a really big deal. Additionally, with Snowpark, our new developer framework, this allows data engineers and data scientists to use their preferred language, executing securely and directly within the Snowflake engine. This really brings a new developer framework to your data that's already in your Snowflake data lake, which again, we think is really huge. Finally, Snowflake offers a governance and collaboration framework for all of the data that's stored inside of your data lake or inside of Snowflake. And this is a really big deal. And I found from talking to a lot of customers, this is often what a lot of people just give up on because they need a data lake in the matter of weeks or months and not years. So this is something that we don't think you should have to compromise on. Snowflake doesn't make it. In fact, we offer a whole suite of benefits to make governance and collaboration really easy. We have built-in views to see what's in your data lake, who's accessing what. We protect sensitive data while retaining analytical value with dynamic data masking. We have built-in security. So we have external tokenization, key rotation, and other features. This is really big because it helps secure your data, which is probably one of your most important assets. And you can easily enrich your data with third-party data in our data marketplace and with data sharing. And I want to talk about that a little bit more. So secure data sharing is a unique aspect of Snowflake, and it has huge implications for storage and data lake and storage patterns. It allows you to give access and essentially share data without any ETL or movement of the data across environments. Within a region, data is never moved or copied. Instead, you can access live, ready to query data. It's also agnostic to cloud provider region. So Snowflake allows you to share data wherever your customers are. With secure data sharing, you can leverage live, transactionally consistent shares and configure refresh cadences down to the minute, saving you money and ensuring durability and availability at all times. I'll come back to this in a minute, but secure data sharing is also really interesting because it allows you, and you may use a data lake or a data mesh, to easily share data with a company either in or an organization inside your own company that might use a totally different storage paradigm or think about their data differently. It doesn't require you to move, copy, export, or mutate the data, which is huge. I've been asked quite a few times, what is our philosophy for how we think about data storage products and kind of our vision for data storage inside of Snowflake? And it's best classified as we design smart storage products. And there are three pillars to what we mean by smart storage. And I want to go into them to give a window into how we think about data storage technology in Snowflake. First, we design industry-leading storage features. So this is the best storage tech to save you the most money, speed up your queries, and ensure that your data is safe. Second, we want to make sure that storage works across the entire platform. So if we design the latest and greatest storage technology, we want to make sure that it works with the rest of the awesome platform features inside of Snowflake. Third, we want to support multiple storage paradigms. And this is something that a lot of people may not know about Snowflake, but I really want to talk about. So we're not trying to force you to pick one specific storage paradigm. Let's take a closer look at each. So I mentioned the first pillar is designing the best storage-specific features. And there's three examples that I want to talk about. This is clearly not an exhaustive list, but it gives you an insight into where our head is at and where we're going in terms of designing the best in storage technologies. One example is our file format. We call it FDN. Our file format is highly compressible. In many cases, it's more easily compressible or better compressed than the leading open file formats. What's really interesting is we're also able to silently and automatically upgrade customers when we have a new innovation in our file format that lowers costs and speeds up queries, all without requiring customers to do anything or change anything. And to me, that is really huge and shows our innovation in thinking about how we store data and also how we're able to deploy new data technologies to customers without causing them headaches and disruption. Second, encryption. It's really common that I've talked to customers who consider encryption in a blob store kind of good enough because going beyond that is really hard. Within Snowflake, each file is individually encrypted using our key rotation encryption mechanisms. This is really huge because it means that the files are not only just encrypted by way of being in cloud, but the files themselves are also encrypted. And this keeps your data really secure and safe. Third, replication. Replication can be really hard, even within one cloud, let alone across cloud providers and regions. Snowflake handles replication within different regions and within different cloud providers. And this saves a lot of time and energy that isn't really giving you value from your data, but it is a core value that Snowflake offers so you can focus your time on what's really important, which is your data, and not necessarily thinking about designing applications or scripts to handle rotation. The second pillar of smart storage is making sure that our great data features, our great data storage features, excuse me, work across the entire platform. So when we have a new storage feature, we want to make sure that it works out of the box with all of the other features that you might use within Snowflake. So this means data marketplace, our data governance capabilities, interoperability with third parties. Saurin's going to talk about a few of these later on in this talk, but I'll quickly give you a few examples. So we've recently launched unstructured data. With unstructured data, we thought about from the ground up that we needed to make sure that unstructured data works with the data marketplace out of the box because customers already use and like the data marketplace. And when we give you new features, we want to make sure that storage features are a platform level feature and interwoven with the rest of the platform, that we're not telling you it's going to come later and that you can't use certain features together. Likewise, interoperability with third parties is something that is really important to us. And Saurin will also talk about this as well. We want to make sure that you can get data in and out of Snowflake as easily as possible. Now, we offer a lot of really great storage features to make sure that your data is replicated and safe when it's inside of Snowflake, but we also want to make sure that Snowflake can flexibly work with your data wherever it may be. The third big pillar of smart storage is supporting customers with different storage paradigms. And this is something that a lot of people may not know or may have misconceptions about within Snowflake. So we don't want to pigeonhole you into one particular storage pattern. We don't want to force you to choose a data lake or a data warehouse. Our goal with smart storage is to design storage features that are best in class, make sure that they work with the entire platform, so that you can use a different set of storage paradigms that work for your organization and your use case. This means that you can create data lakes, you can create data warehouses, you can create data meshes, all within Snowflake. Our goal is to support you and whatever works for you. We've already seen customers such as Siemens, DPG Media, Flexport, and Capital One use a data mesh approach with Snowflake. And if you're interested in learning more about implementing a data mesh with Snowflake, I encourage you to watch the deep dive session from Siemens later today. This is really important when we also think about things like the data marketplace. If you, for example, use a data mesh, but a data provider that you want to work with uses a data lake, you don't need to know that they use a data lake because our storage platform and features allow you to exchange data without having to try and match your storage paradigms, which to me is really important because it allows you to get access to what you need, which is the data itself, without having to think about all of the groundwork on trying to match different storage paradigms. Over the past year, we've been making improvements to Snowflake that support these architectural patterns. They're really grouped in three areas. One, we want to support all data types. We want to give you a platform to use all of your data together. Two, we want to extend access to siloed data, making it easier for you to eliminate silos and bring your data into the data cloud. Three, we want transparent platform optimizations, making the platform better without any user action or disruptions. Now I'm going to hand off to Saurin to talk about some of our recent innovations. Saurin?
Thank you, James. Hello, everyone. My name is Saurin Shah, and I'm a product manager in Snowflake, and I work on the data lake and the smart storage areas. So as James mentioned, these are the three areas of innovation, which is supporting all data types, extending access to siloed data, and transparent platform optimizations. Let's take a deeper look at each of these, starting with the supporting all data types. Since day one, Snowflake has had support for structured and semi-structured data. Snowflake has natively supported these data types and has provided extreme value to these data types, like storing data, governing it, processing it, analyzing, creating metadata out of it, organizing, sharing, replication, and much more. What we want to do is we want to provide the exact same value for unstructured data as well. What this means is we want to provide or make Snowflake a platform that supports all data types, irrespective of the data shape, format, or the size. We give you all the tools to easily and effectively manage your unstructured data. For example, using Snowflake's native governance capabilities, you can now store unstructured data in Snowflake and govern it using the fine-grained rule-based access control. Taking governance one level up, you can now create scoped access for your unstructured data, giving admins peace of mind that they can secure and share their unstructured data. We support something called directory tables, which is a built-in file catalog on top of your unstructured files in storage. Directory table really gives you great capabilities of searching unstructured data and listing the unstructured files from the storage. Not only that, it provides the CDC-like capabilities to build continuous data pipelines for production level scenarios and processing unstructured data. Using secure sharing, customers can now share unstructured data on the Snowflake marketplace and also with their clients, stakeholders, partners, customers, and more. Lastly, we give you capabilities like Snowpark to process unstructured data. Within Snowpark, there are two ways to process unstructured files. One is external functions. So you can send unstructured files to external functions and external SaaS APIs to process the unstructured files and return back structured information so that you can run further analytics on top of that. The other way to process files is via writing Java functions directly within the Snowflake environment. The Java functions run directly on the Snowflake environment, thus giving you capabilities of and taking advantage of the Snowflake warehouse and the scalabilities. Now let's see a quick demo of how you can store unstructured data files in Snowflake and process them using Java functions. In this demo, we are going to see how to manage unstructured data in Snowflake and process that using Java UDFs. For the demo, we are going to use DICOM images. DICOM images are medical images which are very popular in the medical or the healthcare industry. We are going to process the DICOM images and extract metadata from those images, like the patient name, patient birth date, or what was the study about, who was the doctor, who was the referring physician, and all that information. So for that, I have a stage called a DICOM images, and the stage points to my Shah demo bucket with unstructured data and DICOM as the folder. I have a directory enabled on the stage, and the directory has auto refresh equal to true. So what directory table gives is a tabular view of the file catalog or the files in the stage. Let's quickly look at what are the files that are part of the directory. So when I run that, there are about 10 or so images that are part in the directory. Then what I have is a Java function called parse DICOM. The Java function takes in a file as an input, which is the file path, and then it returns a string, which is a JSON representation of all the metadata that we want to extract from the DICOM image. The language is Java, and this is a jar file which contains the compiled version of the Java function. The handler or the class name and the function name is DICOM parser.parse. Let me quickly show you how the Java function is written. So here's the Java function. It's a really simple Java function. It uses a open source DICOM library, and the function, the class name, as I mentioned, is called DICOM parser. The function is called parse. If we see here, the function argument is an input stream, whereas on the SQL side, the function argument was a file. So what we do, or what Snowflake does behind the scenes, is it takes in this file and the URL, it reads the file, it converts that to an input stream and passes the input stream to the Java function. So in the Java function, all you need to do is basically read the input stream and process the file. So I am reading the input stream, I'm creating a DICOM input stream, and then after reading the data set, I am basically just extracting attributes out of that input stream and then creating a JSON of these attributes and sending the JSON back to Snowflake. The attributes which I'm currently getting is all these, which is patient name, patient birth date, what was the manufacturer of the device, patient ID, patient weight, what was the study about, what was the study date, study time, the description, and a few other attributes like these. So as I send the JSON back, it goes back to Snowflake as a string, and then on Snowflake I can just do a parse JSON on the string to extract or to create it into a variant. So let's test the function for all of these 10 images. If I do a select from the parse DICOM Java function with these 10 images, the function actually returned very quickly. It returned in about a couple of seconds. So here is the Java DICOM image and then the extracted metadata from all of these. So let's take an example of this image and let's take a look at all of this metadata. So for this DICOM image in particular, the patient name is all anonymized, the patient ID is anonymized, but we have some information about, what was the image type, what was the study date, what was the study description. Looks like this was a CT scan of the abdomen. And what I can do is I can also retrieve a file URL from this, and then I can very easily go ahead and download that file. So for example, this is the DICOM of the CT scan that we were looking at, the abdomen CT scan. So I can go ahead and download this DICOM image very easily using that URL. Now, how does customers use this in production, or how can they create a continuous data pipeline to keep processing these DICOM images and storing that data? So for that, I have created a stream called a DICOM stream on the stage, which is the images stage. Right now, the stream doesn't have any information because there are no new files that are added. A stream, what it does on the directory table, it gives a CDC like a mechanism to keep track of what are the new files or the unprocessed files that are added to the stage or to the directory, which we need to process. And to process these files, there is a task. The task is scheduled every 2 minutes. It runs on some warehouse, and it runs only when the stream has some data in it. What the task does is the task calls the parse DICOM Java UDF, and it extracts the metadata from the Java UDF, and then it stores into this table called DICOM underscore data. So the schema for the DICOM underscore data is very simple. It just contains a relative file path, a file URL, and the data, which is the variant data that comes in that contains the metadata. Then I have a view over here, or a secure view called DICOM data view, and that extracts out all of these metadata or all of these subpaths from the variant, so that we can get, or the analyst can get, a very simple and a tabular view of all of the metadata. So if I do a select star from this view, I will see that I have the relative file path, the file path, and then I have all the metadata which is extracted from the DICOM images. Now customers or analysts can very easily go ahead and do analysis on top of this. For example, let's say if they want to see the DICOM images where the study description is about knees, then they can very easily write a SQL query and refer to all those DICOM images. Or if they want to basically look at a patient ID or some patient name, they can very easily go ahead and do that. Okay, so we saw a quick demo of how you can store DICOM images and process them using Java functions to extract the metadata from the DICOM images. Snowpark's support for unstructured data starts with external functions and Java UDFs and will expand to Python in future. Now there is no need for separate processing engines because you can just do everything within the Snowflake environment with Snowflake and Snowpark. We saw one use case of processing DICOM images, but there are numerous use cases that customers are enabling right now with Snowflake and Snowpark. Some of these use cases are image classification for images, for OCR recognition on PDFs and scanned documents and images. Customers are also storing audio in Snowflake and transcribing them and running sentiment analysis on these audios. And lastly, customers are also doing natural language processing to process the text which is stored in Snowflake. These are just example use cases, but there are many, many more other use cases which customers are also doing right now on Snowflake. The external functions support for unstructured data is public preview, but the Java function support is private preview. If you are interested in trying out that functionality, please reach out to us or your account executives. Now let's move on to the second area of innovation, which is extended access to siloed data. While there are many benefits of bringing data into Snowflake and unlocking the value, we recognize that eliminating data silos is a journey for many organizations. And that is why we strive hard to make it easier for you to tap into your existing data lakes directly from Snowflake. Earlier this year, we released external tables in general availability. External tables gives you an ability to directly process or query your data on your data lake without ingesting them into Snowflake. We have seen that a lot of our customers use external tables to derive value out of their data while they are migrating their data into Snowflake. Earlier this year, we also added a Hive Metastore connector for our customers coming from the Hadoop environments. While Hive support is great for reaching out to their Hadoop environments, customers have moved on to newer technologies like Delta Lake and Iceberg. And that is why we started working on the Delta Lake connector and Iceberg connector. We are really excited about these functionalities because we are meeting the customers where they are. We in Snowflake, we want to provide you an ability to directly query those technologies or those tables on those datasets. The last area of innovation is transparent platform optimizations. We want to give you a platform that removes complexities and configurations and focuses a lot on simplicity. Since we store the stable format, like how James mentioned, which is the FDN format, we have recently introduced a new optimization to compress that format much more. In fact, compress that format by 35% more. What this means is you pay 35% less storage cost. What this also means is when queries are executed, less data will be scanned, thus you pay less on the query cost as well. Lastly, the other optimization that we have done is query performance on external tables with Parquet data. We introduced a completely new scanner called a vectorized Parquet scanner behind the scenes, and that has improved the scan performance by 7 times as compared to the previous scanner. The fast scan performance has resulted in improving the query performance by 2x as compared to the previous query performance. There are 2 other performance optimizations for external tables that we are working on, and they are in private preview right now. And those are scanning Parquet row groups in parallel and predicate pushdowns to the Parquet scanner. There are some customers who are testing that functionality out and giving us very good feedback. Now I'm going to hand over to Raja to talk about native governance and data governance in Snowflake.
Thank you, Saurin. Hello, everyone. I'm Raja Balakrishnan. I lead product management for data governance at Snowflake. No matter what the architectural pattern that you choose, whether it's data lake, data mesh, data warehouse, or any combination of these, data governance is critical to making sure that your data is secure, trustworthy, and compliant with regulatory requirements. At Snowflake, data governance is all about providing you these capabilities so that you can efficiently and easily govern your data. There are 3 key pillars to governing your data: knowing your data, protecting your data, and unlocking your data through collaboration. We provide multiple capabilities in each of these categories. You heard about a few of those in previous parts of this presentation. Today, I'm happy to share details on a few new capabilities. First, object tagging is now generally available. With this native Snowflake capability, it is easy to know where sensitive data, such as PII or PHI, resides, both for regulatory compliance audits and for appropriate data protection. Tags can be applied to any object in Snowflake, whether it's an external table or an internal table, materialized view, any other object for that matter. But for good governance posture, you need to know more than just the sensitivity of the data that is under your stewardship. You need to know the lineage of the data to ensure its trustworthiness. You also need to know how modifying one object would affect another dependent object. As you heard in the keynote today, we announced in private preview 2 new capabilities to know the lineage of your data and the dependencies between data objects. I will share a bit more about this in the next few slides. But before that, I want to share a few more updates on capabilities to protect your data. Row access policies are now generally available. This native Snowflake capability provides you a policy-based, scalable, and manageable way to meet compliance needs to ensure that only authorized rows of data are accessible to the right users. Similarly, dynamic data masking is now generally available. And dynamic data masking provides a policy-based way to mask sensitive data for unauthorized users while allowing unmasked access to authorized users. With native capabilities like row access and dynamic data masking, there is no need to rely on static ways to protect your data or create copies of data. If you're interested in these governance capabilities, you may also be interested in conditional masking and classification, which provide more granular and automated governance capabilities. Please reach out to your account team if you're interested in participating in any of the private previews. Before we take a closer look at how you can use access history private preview for data lineage, I want to revisit what you can do with access history today. Access history is an out-of-the-box view that contains a record for each select query with information about the tables or views and columns accessed by each query. It also provides information such as the user who executed the query. All this provides the information that you need for various compliance audits, such as SOX compliance or PII access audits. In private preview, we are adding records for data modification commands to access history view. For example, the source stage and the destination table details are logged when a copy into command is executed. Similarly, the source table and the destination table details are logged when a create table as command is executed. As you can see, data engineers can easily use this readily available information to build the lineage between different objects in Snowflake. Let's take a look at the specific use case example as shown in this illustration. Here, stage 1 contains PII information. As a data governor, you're expected to know all the downstream objects that have access to this PII information. Again, as you can see, data from S1 is loaded into table T1, and data from T1 is then available to tables T2 and T3, and finally T3 is available to a stage for further processing. Many of you would acknowledge that this is a tedious task to parse the DML SQL commands in query history to piece together the lineage. With the addition of data modification commands in access history, we provide these details about modified objects in a readily available, easy to query format. As you can see in the simplified output of access history with lineage information, all the relationships between these different objects are very, very easily queryable. We will soon see a demo of access history in action, but before that, let's take a quick look at object dependencies. Another important aspect of knowing your data is knowing the dependencies between objects related by metadata. A few common examples of such dependencies are tables backing a view, or a storage location, such as a stage, backing an external table. Knowing these dependencies is important for data engineers to proactively identify the impact that modifying a table would have on a downstream view. For example, a data engineer might want to notify users of downstream views before he renames a table or drops a table on which the view is dependent. Another important reason to know the dependencies is for data analysts or data scientists to quickly ensure that the view that they use for analytics is backed by a trustworthy table source. To address these use cases, today in private preview, we are adding new dedicated object dependencies view. Snowflake automatically manages all the metadata to describe the dependencies between objects, which is readily available in the object dependencies view for easy querying. As you can see in the simple example in the illustration, external table ET1 is dependent on an external stage S1, and a materialized view V1 is dependent on the external table. The table you see below is a simplified version of the output of a query on object dependencies view. You can see two records providing the dependencies among these three objects. The new object dependencies view provides a new level of visibility that we believe will help data teams proactively assess the impact of modifying an object so they can push changes confidently and completely understanding the potential impact from those changes. Let us now see a brief demo of both access history for data lineage and object dependencies for impact analysis.
In this worksheet, you see 4 data objects: employee info stage, from which data is loaded into a Snowflake table; US employees is the raw table into which data is loaded; data flows to NA employees and all employees tables using CTAS and insert commands respectively. Finally, data is unloaded from the all employees table to an external storage location, which is the employee info backup stage. Now, let's look at how access history can help with 5 different use cases that require data lineage. First, the data governor wants to identify the stage from which data was loaded to the US employees table. Notice that the governor uses base objects accessed and objects modified columns from access history view to identify the source stage from where data was loaded to US employees table. And you see that in the output here. In the second and third use cases, data governor wants to identify the source tables of data to NA employees and all employees. He or she does this by executing simple queries on access history. The key point to note here is that it doesn't matter whether the data flows using a CTAS command or an insert command or any other command for that matter. Access history will have records needed to identify the lineage between objects. In the fourth case, the data governor wants to identify the forward lineage of all employees. He or she wants to identify the target object to which data flows. Note that in this example, since the governor knows that the data is unloaded to a stage, the query contains a filter. It will be perfectly fine to query without providing a target domain filter. The first 4 cases that we saw so far are relatively simple examples to demonstrate how access history works. The 5th use case here is interesting for multiple reasons. You may simply want to document the end-to-end flow of data within Snowflake, or trace back personal information from the destination all the way back to the source, and this might be for something like a GDPR request. For this example, we constructed a query using a CTE on access history, which is the query that you see here. And we will be sure to share queries like this in our user documentation for your reference. And as you can see, this query takes the source object, in this case, the employee info stage, as an input and gives you the lineage starting from this object all the way to all the destination objects to where the data has flowed. And you can see here in this output that you can get the lineage all the way starting from the info stage, which is our source, to the employee info backup stage, which is the destination or the final point where the data is unloaded, and all the tables in between the source and the destination. I hope the short demo helps you visualize how access history can help you address multiple use cases. Let's now move on to object dependencies. Let's use 3 common scenarios that you see here on this worksheet for this demo. First, we see a stage backing an external table which backs a materialized view. So a stage followed by an external table followed by a materialized view. This is the scenario I mentioned earlier in the presentation, which is common for data lake workloads. The second scenario is hierarchical views backed by a table within Snowflake. This is a very common scenario for data warehouse workloads. The third scenario is perhaps one of the most common scenarios where the view is backed by multiple tables. In the real world, this could be dozens of tables. Now let's see how object dependencies view can be used to do impact analysis in each of these scenarios. In this query that you see here, notice that we are using object dependencies to identify the upstream objects that are dependent on the external table, which is the sales staging table. When I execute the query, you see that the sales view, which is a materialized view, is dependent on the external table. Let's now switch to the second scenario, which is hierarchical views. You may recollect that the internal table, which is the sales NA table, has 3 views that are dependent on that table. And if a data engineer wants to, let's say, rename the table sales NA, he first has to analyze the impact of all the upstream views due to that potential change. Object dependencies view can help make this assessment a simple query. Here on this worksheet, you see a simple example query that uses CTE on object dependencies to build a graph of all dependencies on sales NA. As you can see here in this output, you see that North America sales is directly dependent on sales NA, and you also see that 3 other views are indirectly dependent on sales NA table. Let's now take a quick look at our final scenario. You may notice that global sales view is dependent on 2 tables. Let's now run this query. Again, it uses a simple CTE on object dependencies. And let's see, as you can see here, you can identify that global sales is dependent on North America sales, a view dependent on a view, and all that information is available here. And most importantly for this use case, you see that global sales view is dependent on both global sales UK table and global sales NA table, whether it's directly or indirectly. I hope these demos help you think about how Snowflake can help you address your use cases for data lineage and impact analysis.
With that, now back to James.
Thanks, Raja. Let's recap what we've talked about today. 1, we've talked about Snowflake for Data Lake and some of our new storage features. 2, Saurin talked about some of our new unstructured data support and how you can work with unstructured data, which leads to 3, processing unstructured data with Java UDFs. We then talked about reading data with open table formats, specifically Delta Lake and Apache Iceberg. Raja then talked about some of our new governance capabilities, specifically understanding access history and performing impact analysis. We're really excited about all of these new features and capabilities. Which features are you most interested in? Let us know in the comments. Also, make sure to hit the subscribe button and turn on notifications so you'll be the first to know when we put out a new video. For more information, go to signup.snowflake.com. Thanks so much for watching.